Okay, welcome back. Now, before we actually try to find out the Laplace transform of some elementary signals and the associated ROC, we'll first have a brief discussion about the properties of the Laplace transform. Right? And you will see again the properties that we discussed in Fourier transform. More or less, Laplace transform, it also satisfies those properties like linearity, scaling, shifting. So, okay, first property again, it's a property of linearity, and just like Fourier transform, Laplace transform also satisfies the linearity property. That is to say that if I have a signal x1t, it has a Laplace transform of, let's say, x1s with region of convergence, say R1. There is a region in S plane because you don't know the exact nature of x1t, but it will always be a region in the S plane. So we are assuming that it has a region of convergence, that there is a region in the S plane for which the transform, the Laplace transform of this signal converges, and we are denoting that region by R1. And similarly, if I have another signal x2t with the Laplace transform of x2s and a region convergence, say R2, then if I find a linear combination of these two signals, right, something like this, a being the scalar x1t plus b times x2t, and try to find a Laplace transform, the linearity property, it will stay. That is, it will be something like this. Fine. Okay, and then the region of convergence. Okay, that is important. The region of convergence of this combination of signals, it will be actually the intersection of the two region of convergence. If you remember one of the examples that we did, I think it was even like this major region of convergence, right? It was basically the overlapping region or the intersecting region of the two individual signals. Same thing here. Then we had those basic properties. We had time shifting. If we shift in time, what will happen to the Laplace transform? So it may be, again, if I start with I have x of t, it has some Laplace transform, say x of s, and it has some region of convergence r. Then if I shift it by some constant amount t naught, इसका जो Laplace transform होगा, it will have an additional exponential factor, fine, and the region of convergence will stay the same. You can easily prove it. We have proved it in Fourier transform. We have proved it in Fourier series. It is just about substitution, and you will end up at this relation. So I'm not going to spend some time in proving this. You can easily prove it. You can just extend the proof that we used in the Fourier transform. Same kind of analysis, same substitution in this case also. But we also have shifting in the S domain. Fine. Again, this follows from the duality property. So shifting in the S domain is something like this, that if I have a signal x of t, it has a Laplace transform x of s with the region of convergence r. Fine. Then if I shift it in the frequency domain, alternately, if I multiply this signal with an exponential e s naught t, it will correspond to a shift in the S domain, something like this. So this and this is kind of a dual. Fine. और जो ROC होगा, again it will be the original R part, and it may have an additional part which is actually the real part of S naught, because S naught in general is complex. So apart from R, which was the original ROC of x of t, it will now have the additional part which will be the real part of एस नॉट. अगेन यू कैन प्रूव. मैं थोड़ा जल्दी दिखाता हूँ यहाँ पे, बिकॉज आई थिंक we didn't did this kind of property in the Fourier transform. So anyways, it is a simple proof. So this will be minus infinity to plus infinity. आपका जो signal है and then the exponential part of the Laplace transform. So you can combine the two, minus infinity to plus infinity x of t e raised power minus s naught t dt. And this is basically the exponential which determines क्या आपका जो transform है with respect to which variable. So in this case it is x s minus s naught. Like in the normal case, minus infinity to infinity x of t e raised power minus s t dt. यहाँ पे सिर्फ s है argument में, so it is x of s. यहाँ पे s minus s naught है, so it is x s minus s naught. So we call it shifting in the s domain. Fine. So what it means is you have some time domain signal, you have its Laplace transform plus the associated ROC. If to this signal you multiply an exponential signal, then that will result shifting in the S domain with certain modification of the ROC as per this expression. फिर हमारा एक और basic operation था, that was time scaling. Again, same thing that happened in Fourier transform, same thing will happen here with a slight modification of the ROC. So I have a signal x of t, it has a Laplace transform x of s with some region of convergence, say R. And if I define a signal x a t a being the scaling factor, I take the transform. This a will scale the amplitude, it will also scale the frequency parameter as by a. Also, it will scale your region of convergence. Fine. So initially if it was r, it will be scaled down by a factor a. Fine. Again, same proof applies here. You can just extrapolate that proof to this Laplace transform. Okay. Then we again have a famous property of that convolution, wherein we have two signals x1t, Laplace transform x1s, region of convergence R1, then x2t, Laplace transform x2s, region of convergence R2. Fine. And for time domain wave, when we define their convolution, it actually translates to multiplication in the S domain. So this will be x1s into x2s. और जो region of convergence होगा, again it will be the intersection of these two. ठीक है, exactly same thing हमें वहाँ पे भी मिला था in the Fourier transform. Fine. Then there is a property of derivative differentiation in the time domain. So you have a signal x of t, it has a Laplace transform x of s with the region of convergence R. So if you take derivative in the time domain, it actually corresponds to multiplication in the S domain. And the region of convergence, it will be R, huh? Maybe not the entire portion. Yeah, I should have put it like this. ROC, it will have R and maybe some additional part. क्योंकि आप multiply कर रहे हैं S से, it may have its real factor, so maybe some additional part. But in any case, it will always, this ROC will always contain R. कुछ additional भी add हो सकता है. Again, you can easily prove it. So then we have the reverse thing. uh, differentiation in S domain. Again, you can apply the duality property. आपने टाइम डोमेन में डिफ्रेंशिएट किया, फ्रीक्वेंसी डोमेन या एस डोमेन में it meant multiplication by the factor s. So conversely speaking, if you find a derivative in the s domain, it will mean multiplication by some factor in the time domain. ठीक है, so चलिए let's try to have a formal proof for this. So we have this kind of thing, e raised power minus st dt, and if I find a derivative, say d by ds of x s, it is with respect to s, so we will do nothing with x of t, and derivative will apply to this thing. Okay. So minus infinity to infinity x of t will stay. इसका derivative is again e raised power minus st multiplied by the derivative of this, that is minus t, then dt. So this will be minus infinity to plus infinity minus t into x of t e raised power minus st dt, which is, as per the expression, nothing but Laplace transform of this entire thing, minus t x of t. So as we are expecting from the duality property, it will correspond to multiplication in the time. So formally you can put the property like this: x of t Laplace transform x of s with some region of convergence r, then minus times t of x of t Laplace transform d by ds x of s. ROC will again contain r. It may have some part depending upon what value of what t has a value. Okay. Similarly, there is integration. Again, we don't need to prove it. So if we have x of t Laplace transform x of s ROC r, फिर अगर आप इसका इंटीग्रल लेंगे, integral will correspond to division by the factor. वैसे क्योंकि डिवाइड हो रहा है तो रीजन ऑफ कन्वर्जेंस में कुछ कमी आ जाएगी, एंड इट इज़ एक्चुअली इंटरसेक्शन ऑफ दिस आर एंड द रियल पार्ट ऑफ द पैरामीटर एस. फाइन, या आप कह सकते हैं आर इंटरसेक्शन द सिग्मा. So these are some properties. We may be using few of the properties in our, like I said, we'll be next trying to find Laplace transform of some elementary signals. So wahan pe we may be using some of the, yeah, in general, if you have a combination of two or more than two signals, you can use these properties. Right? So okay, we have some time here. So let's try to find the Laplace transform of some elementary signals. We'll do few signals in this video and the remaining in the next video. So these are commonly used signals which we use in signals and systems. तो पहला आपका delta t, fine, which is my impulse function. तो Fourier transform इसका 1 था, तो Laplace transform will be delta t. You can directly use the expression minus infinity to plus infinity delta t e raised power minus st dt. So you know that it is basically equivalent to, because it is defined for, we have that typical property, if you multiply delta t by x of t, so it is actually equivalent to x of 0 delta t. You can use the same property. Yeah, you can solve this integral, no bigger t, so it will be 1. Okay. And ये तो हो गया expression, that's fine, but we are also interested in the region of convergence, जिसके लिए we'll go to back to that property. If it is a finite duration, then ROC is the entire plane. ठीक है, अब ये एक टिपिकली ऐसा सिग्नल है, इट हैज़ फाइनाइट ड्यूरेशन बिकॉज इट इज़ डिफाइंड फॉर वन इंस्टेंट ऑफ टाइम. तो इसका जो ROC होगा, इट इज़ द एंटायर एस प्लेन. फाइन, ठीक है. Then we have another important signal, unit step. If you remember, unit step had a problem with Fourier transform because it was not converging. So you couldn't have directly applied the Fourier transform. But Laplace में ऐसा कुछ है नहीं, so we can directly find the Laplace transform of u of t. So it will be 0 to infinity u of t e raised power minus st dt. Which is 0 to infinity e raised power minus st dt, which will be minus 1 by s. Then you can take e raised power minus st 0 to infinity. Fine. So, but you have to ensure when you proceed to limits, you have to ensure s is greater than 0, which means real part should be greater than 0. Okay, so this will be minus 1 by s. So this will be minus 1, so that will be 1 by s. Fine. और इसका जो region of convergence है, again since it is a right-sided signal, because up to t is equal to 0, its value is 0, and t greater than 0 पे ये define है. So sigma greater than 0 means this part, तो ये आपका ROC रहेगा for this unit step signal. ठीक है. Then you can use the properties that we just discussed. For example, if you have to find the what you call, say आपका पास signal है, say some shifted, say ut minus 3, and it's a unit step function, then you can use the shifting property. ठीक है, जो यहाँ पे है. Fine. So if I apply this property here, we know that u of t, it has a Laplace transform of 1 upon s with region of convergence sigma greater than 0. So time shifting में आपका ROC, it remains the same. So it means u of t minus 3 is equivalent to, as per this property, e raised power minus st naught. So that means e raised power minus, what is s here, 3s into 1 by s, and ROC will still stay there same. ठीक है, तो इसका जो आपका, put it like this, t minus 3 using that time shifting property, yeah, you can directly write it will be e raised power minus 3s divided by s with ROC sigma greater than 0. So we'll stop this video here. Similarly, delta t में भी आप ऐसा ही कर सकते हैं. If you have a shifted delta t function by some amount, you can just use the shifting property. ठीक है. So we'll do some more signals. We will do some sinusoidal signals. We'll try to see what their Laplace transform is, या जो हमारे ramp functions हैं. That we'll do in the next video.